Look around you right now. Light everywhere. You see the world because light enters your eyes, simple. But think about this. Right now, light from every object in this room is traveling in every direction. When you look at something, light from that object reaches your eyes. At the same time, light from you is reaching that object. Light is crisscrossing everywhere, overlapping, passing through the same space. How does that work? How can billions of light rays go in all directions without everything getting mixed up? How do you see a clear image when this chaos is happening? And that's just visible light. Right now, radio broadcasts are passing through this room. Television signals, heat radiation from your body, radar from airplanes, X-rays from space, all traveling through the same space through you simultaneously. All the same thing as light, just different wavelengths. So what is light really? Not the answer you learned in school. That's incomplete, possibly wrong, in ways that matter. The real answer, what light actually is and how it travels from one place to another, is so strange, so unlike anything in everyday experience, that when you finally understand it, the whole world looks different. Let me show you. Imagine you're sitting by a pool. People are diving in. Splash, splash, splash. Waves spread across the water, ripples crossing ripples, complete chaos. Now, imagine a clever insect sitting in the corner of that pool, just sitting there, feeling the water bump against it. The waves hit from different directions, different rhythms, different strengths. Could that insect, just from feeling those waves, figure out what's happening in the pool? Could it tell who jumped in, where they jumped, when they jumped, what's happening all over the pool? Sounds impossible, but yes, in principle, all that information is in the waves. That's what you're doing right now. When you look at something, the light coming to your eye is waves, just like the pool, except three-dimensional instead of two-dimensional. Waves traveling in all directions, crisscrossing, overlapping, a complete mess. And your eye, it's an eighth of an inch hole, a tiny detector, particularly sensitive to waves coming from certain directions, not sensitive to waves from the corner of your eye, unless you swivel your eyeball to move that hole. From this chaos of waves, you extract an image of the world. You figure out what you're looking at from a distance. And here's what's truly incredible. When you're looking at me, someone standing to your left can see someone standing to your right. The light is going this way. The light is going that way. Waves in all directions. A complete network. It's not like arrows passing through each other. It's something shaking the electric field like water height, going up and down. Some quantity vibrating everywhere. The combination of motions so elaborate and complicated that the result produces an influence that makes you see me at the same time completely undisturbed by the fact that there are influences making that other person see someone else entirely. There's this tremendous mess of waves all over space. Light bouncing around the room going from one thing to another. Most objects don't have eighth-inch holes to detect it, so they're not interested. But the light is there anyway, bouncing off this, bouncing off that. All going on simultaneously. And yet, we can sort it out with this little instrument called an eye, the invisible ocean. But that's just visible light. The waves your eye detects, think about those pool waves again. Some are big, some are small. Some are slow, long swells. Some are quick, short ripples. Your hypothetical insect might only study waves between certain sizes. Turns out the eye only uses waves between certain lengths too. Except those lengths are tiny, about 100,000th of an inch. What about the longer waves, the slower swells? Those represent heat. We feel them. Infrared radiation. Our eyes don't see them, but they're there. Pit vipers, snakes in the desert, have a special organ that can see these longer waves. They can pick up mice radiating body heat, see them in complete darkness by detecting infrared. We can't do that. Our eyes aren't built for it. And the waves get longer, much longer. Radio waves, same thing as light. Exactly the same kind of wave, just longer, much longer. Which means right now, sitting where you are, there's not only the light making you see this page. There's also information from radio stations, Moscow radio broadcasting at this very moment. Signals from Peru, radar from an airplane figuring out where it is. All coming through this room right now. Plus X-rays, cosmic rays, all the same kind of waves. Exactly the same, just shorter, faster vibrations. It's all really there. you don't believe it. Pick up a piece of wire connected to a box, a radio. The electrons in the wire get pushed back and forth by the electric field swashing at just the right speed for certain long waves. Turn the knobs to get the swashing just right, and you hear Moscow radio. Then you know it was there. How else did it get there? It was there all the time. You only notice it when you turn on the radio. All these things going through the room at the same time. Everybody knows this, but you have to stop and think about it to really get the pleasure, the inconceivable nature of it all. For centuries, people argued about what light really is. Newton said light is made of particles, little bullets shooting through space, corpuscles, he called them. That's why light travels in straight lines. That's why you can't bend it around corners. Huygens disagreed. Light is a wave, he said, like sound, like ripples in water. Waves spread out, waves interfere with each other. They couldn't both be right, could they? The argument raged for 200 years. Then came experiments that seemed to settle it. Shine light through two narrow slits. What do you see on a screen behind them? If light were particles, you'd see two bright strips, bullets going through slits. But that's not what happens. You see a pattern, bright bands and dark bands interference. Exactly what waves do when they overlap. When two wave crests meet, you get brightness. When a crest meets a trough, they cancel darkness. Light must be a wave. Case closed. Except then someone built a detector sensitive enough to catch individual photons. And what happened? Click, click, click. Individual arrivals like bullets, like particles. But wait, send them through one at a time. Surely a single particle can't interfere with itself. It does. One photon at a time. And the interference pattern builds up. Each photon seems to go through both slits like a wave. So, which is it? Wave or particle? Here's what most people won't tell you. It's neither. Light is not a wave. Light is not a particle. Light is light. We don't have a word for it because we don't have anything like it in everyday experience. We try to describe it using familiar concepts, waves, particles. But those are just approximations, crutches for our imagination. The reality is stranger. Photons are real, individual quanta of light. You can count them. They make detectors click. But they don't behave like little bullets. They behave according to quantum mechanics, which means they explore all possible paths simultaneously like waves spreading out. When you try to observe which slit a photon goes through, the interference pattern disappears. The wave behavior vanishes. You get particle behavior instead. Not because photons are sometimes waves and sometimes particles, but because asking which slit is asking a particle question. And when you ask particle questions, you get particle answers. The photon doesn't decide to be a wave or a particle. It's always itself a quantum object. What changes is how we choose to measure it. This isn't philosophy. This is how nature actually works. And it's far stranger than anyone imagined. So if light isn't particles flying in straight lines, why does it go straight? Here's where things get beautiful. Light takes the path of shortest time. That's Fermat's principle discovered in the 1650s. Out of all possible paths light could take from point A to point B, it takes the one requiring the least time. Sounds simple, but the consequences are extraordinary. Why does light go straight in air? Because a straight line is the shortest distance. And if light travels at constant speed, shortest distance means shortest time. Why does light bounce off a mirror at equal angles? Because that's the path of shortest time between source, mirror, and destination. You can prove it with geometry. The quickest way to get from point A to a mirror and then to point B is to hit the mirror at exactly the angle where the two angles are equal. Now here's where it gets interesting. What happens when light goes from air into water? In water, light travels slower, about 25% slower than in air. So if you're on land and someone's drowning in the water, what's the fastest way to reach them? Straight line. No, you run faster than you swim. So you should run a bit farther on land, even though it's a longer path to spend less time swimming. That's exactly what light does. It doesn't go straight when entering water. It bends. It travels farther in the fast medium to spend less time in the slow medium. This bending is called refraction. The mathematics works out perfectly. The angle of bending depends on the ratio of speeds in the two media. This is Snell's law. But Fermat's principle explains why Snell's law works. Once you understand that light takes the path of shortest time, all sorts of strange phenomena make sense. Mirages on hot roads. You see what looks like water on the pavement ahead. But when you get there, dry as a desert. What you're seeing is skylight reaching your eye by a curved path. How? The air just above the hot road is hotter than the air higher up. Hot air is thinner than cool air. Light travels faster in thin air than in dense air. So instead of coming straight down from the sky to the road, the light can save time by curving through the region where it goes faster. It dips down into the hot layer, speeds up, then curves back up to your eye. You see sky, but the skylight is coming from the road direction. Your brain interprets that as a reflection. Water, here's another one. When you see the sun setting on the horizon, it's already below the horizon. Earth's atmosphere is thin at the top, dense at the bottom. Light from the sun travels slower in dense air. So instead of coming straight to your eye, it curves. It stays higher in the atmosphere longer, where it travels faster, then bends down to reach you. The sun appears to be on the horizon, but it's actually already well below it. The atmosphere bends the light. We see ghosts of the sun. Now let's make something useful. A lens. Suppose we want all the light leaving point P to arrive at point P prime. Focus it. Bring it all together. Light going straight from P to P prime. Fine, that's one path. But how do we make light that goes to some other point also end up at P prime? How do we focus? If light always takes the path of least time, it won't want to take all these different paths. It'll choose the fastest one unless we make all the times equal. That's the secret. A lens makes all paths take the same time. Here's how. Glass slows light down. So, if we take a ray that would naturally go a longer distance, we can insert some glass to slow it down. Make up for the extra distance by adding extra delay. We end up with a piece of glass thicker in the middle, thinner at the edges. All paths straight through the middle, angled through the sides, take the same time. That's a lens, a device that equalizes travel times. Same principle works for mirrors. Want to collect starlight from billions of miles away and bring it to a focus? Make a curved mirror. Shape it so that light hitting anywhere on the mirror takes the same total time to reach the focal point. That shape is a parabola. The Huygens Palomar telescope uses exactly this principle. All optical instruments, telescopes, microscopes, eyeglasses work by manipulating travel times, making some paths faster, some slower to control where light goes. But here's the deepest question. How does light know which path takes the least time? Does it somehow sense the nearby paths, check them against each other, choose the best one? The answer is yes. In a way, that's the feature you can't explain with straight lines and rays. That's where wavelength comes in. The wavelength tells us approximately how far away the light must check other paths. It's hard to demonstrate with visible light because wavelengths are so short. But with radio waves, say 3 cm waves, the effect is larger. Put a source, a detector, and the slit between them. Radio waves go from source to detector through the slit. Fine. Make the slit narrower. Still works. Now move the detector to the side. The waves won't go there through a wide slit. Why not? Because they're checking several paths nearby, and those paths correspond to different times. The waves interfere with themselves, cancel out, but close the slit down to a very narrow crack. Now there's only one path available. The waves have nothing to compare against, so they take it. With a narrow slit, more radiation reaches the sideways detector than with a wide slit. You can do this with light. Here's how. Find a small bright light, a distant street light, or sun reflection in a car bumper. Hold 2 fingers in front of one eye. Look through the crack. Squeeze your fingers together gently. The light, which was a small dot, becomes elongated, stretches into a line. And if you look carefully, you'll see fringes, bands along the edges, colors. Why? The fingers are very close together. The light spreads out at an angle. It comes into your eye from several directions instead of one. This is light not going in straight lines, light checking nearby paths, light behaving like a wave. So, what's actually happening? What is light really doing? Here's the modern understanding, the quantum mechanical picture. Light is made of photons, real particles. Detectors click when they arrive. The brightness of light is proportional to the number of photons per second. But photons don't travel like bullets. When a photon goes from A to B, It doesn't take one path. It explores all possible paths simultaneously. For each path, you draw a little arrow, a complex number. The angle of that arrow is proportional to the time that path takes. The faster the light oscillates, the more the angle rotates. That's frequency. Different paths take different times, so the arrows point in different directions. Now add up all the arrows, all possible paths. The probability that the photon arrives is proportional to the square of the length of the sun. Here's what happens near the path of least time. The time doesn't change much as you vary the path slightly. So arrows for nearby paths all point in roughly the same direction. They add up, reinforce each other. Far from the path of least time, small changes in path produce large changes in time. The arrows point all over the place. They cancel out, form a tight spiral. Almost all the probability comes from paths near the minimum time. That's why light follows the path of least time. Not because it only takes that path, but because all the paths far from it cancel out through interference. This explains why you can block part of a mirror, and it still reflects almost normally. You're just removing some of the arrows from the spiral ends. The central cluster near the minimum time path is what matters. This is the connection between the photon picture and the principle of least time between particles and waves between quantum mechanics and classical optics. Light takes all paths, but only paths near the minimum time contribute significantly. Remember those pool waves, different sizes. Light comes in different wavelengths, and we give them different names. The longest waves, meters to kilometers long, are radio waves. AM radio, FM radio, TV broadcasts, all electromagnetic waves, just very long ones. Shorter, centime to millimeters, microwaves, radar. Shorter, still fractions of a millimeter, infrared heat radiation, what you feel from a hot stove. Then visible light, the tiny range our eyes detect, about 400 to 700 nanometers, 4 to 7/10 of a millimeter. Blue is short, around 450 nanom. Red is long, around 650 nanom. Shorter than blue, ultraviolet, what gives you sunburn. Shortest still X-rays, what doctors use to see your bones. Shortest gamma rays from radioactive decay and cosmic events, all the same phenomenon. Electromagnetic waves oscillating electric and magnetic fields propagating through space. The only difference is wavelength is frequency. Different wavelengths, different properties. Radio waves pass through walls. Visible light doesn't. X-rays pass through flesh. Visible light doesn't. But it's all light. All electromagnetic radiation. All the same thing. And it's all in this room right now. Radio signals from thousands of stations. Infrared from everything warm. Visible light bouncing around. Ultraviolet from the sun. Cosmic rays from distant galaxies. All the same kind of waves. All coexisting. All passing through each other without interfering. A complete network of vibrating fields filling every point in space. So what is light? Not a wave, not a particle. Light is light. We don't have a word for it because we don't have anything like it in everyday experience. It's a quantum object. When you're not looking, photons explore all paths, interfere with themselves. When you detect them, they arrive as discrete quanta clicks in a detector. Both are real, both are true. There's no contradiction, just two aspects of the same quantum reality. We evolved to understand everyday objects, things we can hold. Light is none of those. Light is something else. But we can understand it by following the mathematics and experiments, and they lead somewhere strange and beautiful. Think about what's happening right now. Photons from the sun, infrared radiation from everything warm, radio waves from hundreds of stations, X-rays from space, cosmic rays from distant stars, all passing through the same space at the same time. A tremendous mess of waves, and yet we can sort it out. Tune a radio and hear a single station. Look and see a coherent image. Everybody knows electromagnetic waves fill space, but you have to stop and think about it to really get the pleasure, the inconceivable nature of nature itself. When you understand what light is, really understand it, the world is far stranger than it appears, far more beautiful. And that's what physics is about, expanding our intuitions to grasp nature as it actually is. That's the beauty of it, the terrible, wonderful beauty of understanding.